So, good evening, everyone, and welcome to the second session of a series of lectures on steel structures. Uh, I, I, I believe that most of you have uh, participated in yesterday's session. So, yesterday we covered the basic concepts of structural steel design, all the basic premises that we need for regular design of uh, individual structural components, like for design for tension, design for compression, design for flexure, design for shear, and design for torsion. And the building code requirements that provided in BNBC 2020, we have uh, somewhat touched upon those topics. Now, today is kind of advanced uh, part of this lecture. So there are many other topics that actually that should be covered. And my intention was to cover many topics, but finally I've realized that it's very difficult to cover all the topics that are mentioned in the code. So I had to be selective. I have uh, I have selected basically three topics, uh, some uh, some aspects of connection, and then direct analysis method and seismic provisions. Now, to be honest, if I want to do justice to any of these topics, I should devote the whole lecture only on one topic. But as you can understand, that we want to get a flavor of all these different topics. So I'll touch upon these three topics. I had no other choice but to leave many other topics like evaluation of existing structure, design for serviceability, and inelastic design of steel structures. So I couldn't cover these topics. So hopefully in future, in another occasion, we can cover those topics. Now today, let's start. Okay, so I'll start with connections. So yesterday we talked about different the classification of connections, like simple connection, fully restrained connection, partially restrained connection. Today we'll talk more about how we connect different elements of different members and what are the ways. So basically there are two ways. One is welding and another is bolting. Now, first let's talk about welding. So there are different types of welding, but for in the building code, basically these three types of welds are mentioned. One is groove weld, as shown in the left picture, that we first create groove in the parent material, the members that we want to connect. We prepare a groove, then we weld on that groove. That is groove weld. Second type is fillet weld. So we place the members one upon another in different angles. They may be in different angles. It's shown here is in right angle, 90 degrees. So we can place one plate on another plate like this, and we weld from the side. That's fillet weld. The third type is plug weld and slot weld. Plug weld is like we keep a hole in we keep a hole in one plate, and we weld in that hole and create a plug. so that one plate doesn't move from another plate. And the hole may not be just circular, it can be elongated. In that case, we term that slot weld. So these are different types of welds. Now, groove weld, there can be three types of groove welds. One is complete joint penetration groove weld, CJP, where we weld from the bottom of the thickness, from the bottom, and we gradually come to the top of the weld. And usually we keep some material below bottom and some material above top, and then we grind. So that is complete joint penetration. And partial joint penetration, when there's a situation that we cannot go to the bottom of the thickness, we leave some part of the parent material at the bottom. We don't weld the full extent of the thickness. That's called partial joint penetration weld. And flare weld is when we have situation like one member, one plate is bent on another, or both the plates may be bent from both sides. Then at that joint, if we weld, that is flare weld. So these are different types of groove weld. Now, uh, groove weld we can have in four different positions. One is flat, when both the plates are horizontal, flat in the same plane. Another is horizontal position, that the plates may be in an inclined position or vertical, but the axis of the weld is horizontal. The second picture, that is horizontal position. The plates are vertical, but the weld, the alignment or the axis of the weld is horizontal. That's horizontal position. And vertical position is when the weld itself is, the alignment or the axis of the weld is vertical. That is vertical position. Overhead position is like if we want to weld from bottom under a roof like that, or the top flange where of or after we are welding from the bottom, situation like that, that's overhead position. And these are different positions of groove welds. And partial joint penetration can be of different types. From the shape of the groove, we term them J groove, V groove, U groove, or bevel groove. Among them, V groove and bevel groove, they're straight cuts. But the angle of these cuts may be different. V groove may be 45-degree V groove or 60-degree V groove. Similarly, bevel groove can be 45-degree bevel groove or 60-degree bevel groove. Now, the process of welding. There are different processes of welding. The most usual one that we see the size where we have an electrode, stick of electrode, that's called shielded metal arc welding, SMAW. So that's the manual arc welding that we quite often see at the sites. Another one is gas arc metal welding. Here an inert gas, metal inert gas, MIG wire is used as electrode. The electrode itself is that is MIG electrode, and between the electrode and the base metal, arc is formed. So we'll have pictures and we'll see that what are the differences. Flux core arc welding. This is automatic type. We have machines. We need machines for this type of welding. The electrode is tubular. like tube, and it contains flasks, and there is constant voltage, so that's why you need a machine for that. There can be two types of shilling. One is FCAWG, another is FCAWS. In FCAWG, the shielding gas is supplied through a gas nozzle, and in FCAWS, shielding gas is obtained exclusively from the flux. It comes from the flux. Another type of arc welding is submerged arc welding, SARW. That is, usually you can find this type of welding in the factories, not at the sites. So this is submerged type. Let's see some pictures. So at the top left, that's a stick welding, that SMAW, that is usual type of welding, manual arc welding, that is the top left. Top right, bottom left is the that is with MIG, metal inert gas welding. So you see the electrode is inside. Electrode is number 3 here, inside a tube, and that tube is connected to the electric supply. So a little bit different, but that is also doable at sites. And top right is the FCAW type. So if we have a gas nozzle, then this is FCAW G type. So we have a gas nozzle and flux core wear, and arc is produced. This is also doable at the site, but you need a machine for this. It comes with a machine. And the bottom right is the submerged type, submerged arc welding, SAW. So you need big facility for that. You cannot do that at site. Usually that's done at factories. So these are different types of welding. Why am I saying all these? Because we have tables in our code where, depending on the welding process and the position of groove weld, and for partial joint penetration, PJP type of or groove welding, depending on the type of PJP, we have to define the effective throat. Now, why we need the effective throat? From the effective throat, we can calculate the effective area of welding. Why do we need effective area of welding? To calculate the capacity of welding. So basically, at welding, shear is generated, and we have to multiply the shear strength with the area, then we'll get the capacity. So for that, we need to define the effective throat. Multiplied by the length is effective area. So to determine effective throat, we need to know what type of welding is this, what position of welding is this, and what is the welding process. Then only we can define the effective throat. In most of the cases, effective throat is the depth of groove, but in some cases, like for usual manual welding, if the bevel, if this is PJP, usual manual type welding, for any groove location, we have to deduct 3 millimeters from the depth of groove, like that. So we need to consult this table to calculate effective throat. Now, for flare bevel groove and fair V groove, there is another table. Depending on the radius of flaring, we can calculate the effective throat size, effective weld size, that is effective throat. Now in BNBC we have requirements of minimum weld size. So depending on the thickness of the base metal, we have to know what should be the minimum effective throat thickness. This is minimum. We can provide more. It will come from our calculation, but there is a minimum. If from calculation we need less amount of welding, we cannot do that. We have to give this amount. This is the minimum. So for different depths and depending on the welding type, like the upper table is for PGP, groove weld, and the bottom one is for fillet weld. And to calculate capacity, there is our code comes with another table, and in this table, depending on the filler material, we know the electrode is the filler material for the stick weld. Depending on the filler material and the strength of the filler material and welding type, we can get the strength of the welding material. Like for here, this is for PGP, partial joint penetration. It shows what should be the value of capacity reduction factor, what should be the value of safety factor, and what should be the value of strength, Fy or 0.6 Fy. So it's given there. And what section in the code should we follow to calculate the capacity? It is also given in this table. So like this is the table. Now that was about welding. Now we'll talk a little bit about bolts. So mainly high strength bolts, that in while defining bolts, type of bolts, the code only talks about high strength bolts. So the specification for high strength bolt specifications are either A325 of ASTM or A490 of ASTM. Okay, and with bolts, we can have two types of joints. One is slip critical joint, and another is bearing type joint. Now, this is important. Slip critical joint, where we get the strength through the friction of the two materials when they are clamped together very tightly. And it is very important to have good surface of the base metals to have this slip critical joint. So the surface preparation is very important. And so this slip critical joint, we pretension the bolt and tightly clamp the bolts with the metal plates. And from that, just by friction, it is so tightly clamped that the friction between those two plates actually gives us the resistance against any movement. But in bearing type joint, the clamping is not that tight. And the surface, we cannot depend on the preparation of surface is not that good that we can depend that the friction of the surface will give us the complete resistance. We have to depend on the bolt, that is the shear resistance of the bolt and the bearing resistance of the bolt. So we have to depend on the bolt. That's why it's called bearing type joint. Here, let's talk about them. Then for bolting, first we have to drill holes. So what should be the hole size? You see, there are 4 different types of hole sizes. For different types of bolt diameters, like M16 milli, 20 milli, 22 milli, the standard size is always 2 millimeter more. The diameter is always 2 millimeter more than the bolt diameter. That is the standard usually. For bigger bolts, it's 3 millimeters more. But sometimes we have to drill more, like oversized holes. Those are 4 millimeters bigger in diameter than the bolt size. And there are other types like short slot and long slot. That is, they are not circular, they are elongated, oval shaped. Like short slot, the first one for M16, we can have 18 millimeter, just like the standard diameter in one direction, and in the other direction that may be 22 millimeter. And so this is like a slot. And that slot can be longer. It can be as long as 18 by 40 for the first one, M16. So we see there are different sizes of holes. Now, the code says oversized holes are permitted in any or all plies of slip critical connections, but they shall not be used in bearing type connections. So this is important. That usually most of the cases we design bearing type connections, but for special moment frames we cannot design for bearing type connections. We have to go for slip critical joints, but usually we design for bearing type connections. For bearing type connections we cannot have oversized holes. That's restricted. For slip critical connections, if we have oversized holes, then the washer, in the code there are specifications of washers, standard washers. So I didn't cover those, but there are specifications for standard washers, fasteners, all the accessories, there are specifications. So for oversized holes, we cannot just use standard washer, we need to use hardened washers. Short slotted holes are permitted in any or all plies of slip critical or bearing type connections. We can use short slotted holes. The slots are permitted without regard to direction of loading in slip critical connections. In slip critical connections, we can place the elongated direction in any direction, elongated side in any direction. But for bearing type connections, the length shall be normal to the direction of the loading. As we know, in bearing type connections, we have to depend on the bolt. So in the direction of loading, we depend on the base plate is in touch with the bolt. If there is gap, then there will be a lot of deformation, right? So if we place the elongated part along the elongated side along the direction of loading, then there will be no touch. There will be gap from the bolt and the base metal plate. That we cannot allow. So we have to be very, very careful while placing the holes. We have to consider the direction of loading in case of bearing type connections. Long slotted holes are permitted in only one of the connected parts of either a slip critical or a bearing type connection at an individual fane surface. That is, we can, you see, there will be holes on both the plates, but in only one plate we can have long slotted holes. We cannot have long slotted holes on both the plates. So that's a requirement. Long slotted holes are permitted without regard to direction of loading in slip critical connections, but shall be normal to the direction of loading in bearing type connections. So the same thing is applicable here also for long slotted holes too, that the elongated side must be perpendicular to the direction of loading. So minimum then we minimum spacing and edge distance, right? So what should be the minimum spacing of holes, bolts, center to center distance of bolts, and what should be the minimum distance from the edge of the plate? The distance between centers of standard, oversized, or slotted holes shall not be less than, there's some mistake, 2 times the nominal diameter d of the fastener. A distance, this is wrong. Actually, it should have been 2.5 probably. Oh, sorry, 2 and something is wrong here. 2 point something. I don't remember. It probably is 2.5 times the nominal diameter d of the fastener. But 3D is always preferable, and usually what we practice is 3D. Now, minimum edge distance is tabulated in this table. So depending on the bolt diameter and what type of edge is the plate has, it depends on that. If the edge is sheared, that if the edge is produced by cutting the plate, then that is a sheared edge. Or if the edge is a rolled edge, that is while manufacturing, during the rolling process the edge is created. It is not created afterwards by cutting the plate. So depending on the type of the edge, we have different minimum edge distance. When the edge is created by cutting a plate, then we have to leave more space between bolt hole and the edge. Okay, so this is very important. For built-up sections, we have to be very careful because built-up sections are usually uh, produced by cutting plates. Now, edge distance increment, that is for slotted holes, we have, and oversized holes. Those were these were for standard holes. These measurements. But for oversized holes and slotted holes, we have to leave more space. Like for oversized holes, 2 milli or 3 milli more distance we have to leave. And for slotted holes, it is tabulated here. The maximum distance from the center of any bolt or rivet to the nearest edge of parts in contact shall be 12 times the thickness, that is the maximum, of the connected part under consideration, but shall not exceed 150 millimeters. So if we are connecting something, so the distance of that connected part from the edge should not be more than 12 times the thickness of the connected part. Okay. This is important when we say attach bracing with a gusset plate. Then in the gusset plate, from the edge of the gusset plate, the bracing, what should be the distance? We should follow these recommendations. Now, pretension or snug tightened high strength bolts. So we have discussed about slip critical joints. So for slip critical joints and even for bearing type of joints, we have to pretension. We have to give tension. We have to give tension in the bolt so that it is tightly, the plates are tightly clamped with one another. So we can give that pretension with a wrench, like power wrench. So electric type of power wrench, or we can use a manual method. When you use a manual method, it's called snug tight. Now, the definition of snug tight is the snug tight condition is defined as the tightness attained by either a few impacts of an impact wrench or the full effort of a worker with an ordinary spud wrench that brings the connected plies into firm contact. Okay, so the worker has to give his full effort, then that will be snug tight. Or we can use the impact wrench. So these are the nominal stress of fasteners that we use to calculate the capacity. So for tension capacity, we use FNT, and to calculate the shear capacity, we use FNV. So different types of for different types of bolts, and whether threads are there at the shear plane, depending on that, the capacity is changed. For example, if we have a 325 bolt with threads not excluded from the shear plane, so we have in the shear plane you have threads, so the effective area is less. In that case, the nominal shear stress is 330 megapascal. But if there is no thread in the shear plane, then that is 414 megapascal, like that. Okay. Now let's talk about tension and shear strength of bolts. We have just introduced FNTF and FNV. We have to multiply with the area of the bolt. So now you can say that, but in the bolt there are threads. We should have considered effective area that is already considered in that table. So we just have to multiply with the area of the bolt. Okay, and now the strength reduction factor and safety factor, resistance factor and the safety factor, they are mentioned here, 0.75 and 2. Now, when there is combined tension and shear, so when there is tension, and if there is tension and then you shear something, the shear capacity becomes very big, gets reduced. So when they are simultaneously applied, then the capacity gets reduced. So those equations are given here. So high strength bolts in slip critical connections. So the nominal strength depends on a number of parameters: mu, du, HSC, TB, and S, number of parameters. So mu, this is very important. This mu, this is we know that mu stands for friction coefficient. Here is actually friction coefficient is called mean slip coefficient. It depends on surface. So surfaces are defined for slip critical connections in two classes, class A and class B. Class A is the surface that is perfect, that is if the surface is as fresh as it is just manufactured. So if we can prepare a surface, or just after manufacturing we put a slip joint, then the surface is class A. And class B surface is not like that, but still in the code there are provisions what type of treatments should be there. So class B is not as fresh as just manufactured at the factory. So for them, we have different slip coefficient, and HSC DU 1.13. I don't remember right now what is DU is for. I have to check. I just forgot. HSC is whole factor determined as follows. For Type of hole, standard or oversized or long slotted or short slotted. HSC stands for that. And okay, TB. TB is bolt tension, tensile strength of bolt. NS is the number of plies, the number of slip surfaces. Okay, I have to check what is DU. Now, bearing type bolts, I think you are familiar with these. There can be bearing type failure, that is at the bearing surface, it may yield, and there may be tear out type of rupture if it is close to an edge. So from the edge, if for tearing, the effective area is LC, that is the distance from the edge and the thickness. And for bearing type, it is DT, that is the diameter of the hole, and T is the thickness of the plate. So DT is the effective area. So for bearing type of bolts, so we have two criteria for each case. When deformation at the bolt hole at service load is a design consideration. Uh, at service load, if we consider that there can be no deformation of the bolt, then there are two criteria, you see. One with LC into T, that is related to tear out, and another is D into T, that is related to, so 1.2 LCTFU, that is related to tear out, and 2.4 D into T into FU, that is related to bearing type. So in each case, we have these criteria, different types of criteria. When deformation at the bolt hole at service load is not a design consideration, so if we allow some deformation at the bolt hole, then we have higher limits. Sorry, we have to go for the second one is that we do not consider, we do not allow, so we have to go for higher capacity. Sorry, no, the second one is we have higher limits, so we allow some deformation. And for long slotted holes, we have different equation. So those were some tips, rather I should say some tips about connections. So the tables that are provided in the code, how to consult those tables, I have just given those tips. So different types of welds and welding processes, based on them you can determine the throat size, and then you calculate the capacity. And for bolts, depending on the different types of bolt holes and different types of joints, slip critical or bearing type, how to calculate the capacities. So these were some tips to for you. Now that was one topic. I am going to talk about the next topic, which is direct analysis method. If you remember, yesterday I showed you one hierarchy that analysis, we can do analysis in two ways: elastic analysis and inelastic analysis. And then I said that in elastic analysis there can be uh, first order analysis and second order analysis. And in the second order analysis, we can go for effective length method. First order analysis can be also effective length method. And another second order analysis, direct analysis method. So usually our usual practice is to go for effective length method, having K. We have to determine K. We have to we have to understand what should be the value of K, which is effective length factor. So our buckling analysis depends entirely on that what is the effective length. But in direct analysis method, the method was developed actually to avoid that problem. It is sometimes quite tricky to actually judge what should be the effective length factor, and it depends, the whole analysis depends on that. So to avoid that way, this direct analysis method was evolved, and that's why probably in this method K is always 1, effective length factor is always 1. You can wonder that why, and then how we deal with buckling. Let's see. So this method is a rational approach to stability analysis and design. Why is it a rational method? We'll discuss. Second point is P delta, P large delta, and P small delta effects are accounted for through second order analysis. Both are accounted for. In our effective length method, we also account for both of these effects using B1 and B2 factors. Here we treat it in a different way. Geometric imperfections are accounted for through direct inclusion in analysis model or by applying notional loads. Now we'll talk about notional loads. Yesterday we didn't talk about notional loads. What is notional load? Now you can understand this is something related to geometric imperfections. So we consider geometric imperfection in direct analysis method by notional loads. We'll discuss about that. Now, fourth point is inelastic effects such as distributed plasticity are accounted for using flexural and axial stiffness reduction. This is very important. In this analysis method, we reduce the stiffness, flexural and axial stiffness. So that is one trick of this method. And since we consider all the second order effects, and by that we actually get the buckling capacity, we don't need to artificially change the length using a length or effective length factor. So K is always 1. We don't need to worry about K anymore. So if we compare, so the major difference is that in effective length method, nominal EI and EA stiffness values for flexural and axial stiffness values are used. In DA, we reduce them. Notional loads, originally in effective length method until 1989, there was no notional concept of notional load in effective length method. Later, in effective length method, notional load was introduced. We mentioned about this 0.002 yi yesterday when we discussed about effective length method, but we didn't call it notional load because the code doesn't call it notional load. But this is actually kind of notional load because in the ALM method, this was introduced to deal with the geometric information to some extent. So, but in the effective length method, this is prescribed as the minimum lateral load. So if the lateral load is more than this value at any level, any story level, then we don't need to add any extra load for geometric imperfection. But in direct integration, direct analysis method, this is different. The value is same, 0.002 yi. Yi is the gravity load at some story level, ith level. So the value is same, but the treatment is different. Like for when there is less second order effect, then this is the minimum. We don't need to add to the existing lateral load, other types of lateral loads. But if the second order effect is bigger, then we have to add this value with other types of lateral loads. So then this is additional. This is called notional load. And the K value is always 1 for direct analysis method. So what happens in the effective length method, the calculation is such that we always kind of overestimate the axial force, and we have less amount of moment. So from the left picture, you can understand if the difference between actual response and the analysis results. In the left picture, the interaction curve is shown, and the thicker line, that is the analysis result, that intersects at some point. So that is the capacity. So the capacity of, we overestimate the axial capacity and we underestimate the flexural capacity. Okay, so that's the problem. But in direct analysis method, the method is developed in such a way that it at the ultimate level, when it reaches the capacity, then the actual capacity and the direct analysis method predicted capacity is very similar. So it was developed in that way. But for other limit states like serviceability limit state, then they will be different. In case of elastic effective length method, in the other service other limit states, they are very close to actual response. But in direct analysis method, at the ultimate limit state, this is close to the actual response, but in other limit states, this is not so close. So that's a big difference. So these are the points that we have to remember to apply direct analysis method. We have to model the frame behavior accurately. So this is not so difficult. We are used to modeling using finite element method based software. So if we model in that fashion, that is okay. That is the accurate model. But if we go for like 2D analysis, a few years ago, many designers of steel structures, they used to model 2D frames and then analyze. That is not accurate. That causes problem. Second important issue is that we have to factor the loads. For LRFD, this is not a problem. We always factor with overload factors. But for ASD, since the whole method is based on the ultimate limit state, so even for ASD, we have to first multiply the what do you call it, ASD load combinations with 1.6, and after doing all the calculations, the results are then we have to divide the results with 1.6. So if we want to follow ASD method, then that's the problem here in direct analysis method. Even the ASD load combinations we have to factor with 1.6, because at the end we'll divide the results with 1.6. Third important point is that consider initial imperfections. So we can consider initial imperfections in two ways. One is while modeling our frames, we can provide some initial sway, initial drift at different levels. Very small drift. If we want to consider initial imperfection, we can apply some very small amount of drift at different levels. Or without doing that, we can model as usual, and then we can apply notional loads, which will reflect the effect of initial geometric imperfections. Fourth point is reduce all stiffness that contributes to stability. So there are factors by which in this method in the code those factors are given. We reduce the stiffness, EI and EA, flexural stiffness and axial stiffness. And then second order analysis is conducted where both P large delta and P little delta, both type of effects are considered. I'm sure that many of you are quite familiar with software like SAP or ETABS or STAD, and you have inbuilt functions in those software that can deal with that. So that's not a problem. And to use direct analysis method, we have to use, to apply direct analysis method, we have to use software. So software will take that into account. Now, K is always 1, that is not a problem. And the last point is for serviceability checks, we have to use unreduced stiffness. So we have to run our models many times. I'll explain why we have to do that. And for serviceability checks, we cannot reduce the stiffnesses. So stiffness unreduced stiffness values will run and check the serviceability limit checks. So these are some important points that we have to remember while applying direct analysis method. So the model has to be accurate. What do we mean by that? So you can see this is nothing but usual finite element modeling, which many of us are used to. And the advantage of this is that for a certain direction, there are columns that will contribute in resisting the lateral load. But from other grids, there will be columns which is called leaning column, which will not contribute, which may not contribute to the lateral load, but they have to undergo the same amount of deformation with the whole structure. And those columns, since those columns are gravity load bearing columns, they will have gravity loads on them, and then they will undergo deformation, side sway, that will cause P delta effect, and that will contribute to the second order moments. So that's why if we model the frame in 3-dimensionally, then we can get that picture. Otherwise, we do not get that picture. 2-dimensional models are not good for direct analysis method. So I think this is not a problem for us. Very few people use 2-dimensional models anymore. Now, factoring loads. For ASD, as I have already said, we have to factor the ASD load combination with 1.6. For LRFD, we can use normal LRFD load combinations, strength design load combinations. But very important thing is that in elastic analysis, what the software does is that it analyzes the structure for dead load, it analyzes the structure for live load, it analyzes the structure for wind load, earthquake load, and then after all these analyses, they're combined, the results are superposed. But that superposition is not valid for direct, since we will consider P delta effects, both types of P delta effects, that kind of superposition is no more valid. So we have to combine all these combinations. Like we cannot have run for separately for dead load and run separately for lateral loads. We cannot do that. We have to combine them, and that will be one case for running, because all the loads, both lateral load and gravity load, must be present to take P delta effect into account. So that's very important. And now how we can consider initial imperfections, geometric imperfections into account. There can be two types of geometric imperfection. One is the out of straightness of members. Okay? That is somewhat taken into account by reduction of stiffness. And another is out of plumbness, that is it is no more completely vertical. There may be from one story level to another story level, there may be a little bit of out of plumbness. And that we can consider in two ways, the out of plumbness. While modeling, we can model it in that way, that the levels are not vertically upright. There may be some out of plumbness. That's one way. Another is to consider by reducing the stiffness. Oh, sorry. Another one is by applying notional loads. Now, what are the notional loads? Notional loads are these loads. They are lateral loads. And this is very small amount, only 0.2% of the vertical load, gravity load. So at each level, say level yj, the lateral load at that level will be 0.002 yj, and like that. So, and these notional loads are actually to account for geometric imperfection and other types of non-ideal conditions. Lateral loads applied at each framing level, specified in terms of gravity loads at that level, applied in direction that adds to destabilizing effects. So we have to independently apply in X direction and then in Y direction, in both the directions, independently. Need not be applied if structure is modeled in an assumed out of plumb state. So if we model the structure as out of plumb, in the out of plumb state, then we don't need to apply them. But usually we don't model out of plumbness, we apply these notional loads. So how to apply the notional loads? Consider initial, these notional loads are actually for to consider initial geometric imperfection. And the notional loads can be applied as loads or notional displacement. Usually we apply for as loads, notional loads. Here you see the factor for LRFD, the factor is 1, and for ASD, the factor is 1.6. And the last thing is very important. If the second order sway divided by the first order sway ratio is less than 1.7 for reduced stiffness, or for nominal stiffness without reduction of stiffness, if it is less than 1.5, then if at a particular story level the existing lateral load for other sources is more than 0.002 y, then we don't need to add this. This is the minimum lateral load condition if the second order effect is not that much. If these sway ratios are more than these limiting values, then we have to add these notional loads with other lateral loads. So if we have wind load, earthquake load, whatever lateral load, we have to add this 0.002 yi. if the sway ratio is more than these limited values. So that is very important. Now, why do we reduce the uh, stiffness? One reason is to consider the residual stresses. Usually the steel sections, the way they're produced, depending on how they're produced, they have some amount of residual stresses. To consider those residual stresses, we reduce the stiffness value, stiffness reduction. Now, how much do you have to reduce the stiffness? EA, that is axial stiffness, we take 80%, and EI depends on the axial force that is coming onto the structure. If the axial force is much less than the axial capacity, then we just reduce 80%. If the axial force is more than that, then there are some formulas that we have to calculate. So that is important. And remember, during the process of deformation, the axial force, these values vary, and usually the software in every increment of deformation, it calculates the amount of axial force that's coming onto a particular member, and incrementally the stiffness, a flexural stiffness is adjusted. Okay. So that is it. We can do another thing. We can always consider tau b as 1 if we, instead of applying notional load as 0.002 yi, if we apply 0.003 yi, then tau b is always 1. That we can do. This one is important. This was important to consider the p little delta effect. To accurately for accurate analysis of p delta effect, we have to mesh the columns. This is interesting. Usually the beam column elements that they're in the software, in any software like ETAP, SAP, STAT, whatever, the beam column elements are perfect, are exact. That is, we don't, to get exact solutions, we don't need to mesh beam column elements. So that's why usually we don't mesh beams or columns. We mesh slabs or we mesh walls, but usually don't mesh beam columns. But to get the P delta effect, P little delta effect, we have to mesh the columns. We don't need to mesh the beams. We have to mesh the columns. So this is important. So it depends how fine meshes you want to use, but like at least there should be 4 divisions in each column, in each story level. So okay, this is important. Reduction factors like EA and EI after the design, like initially we don't have the design, right? So we design and we go for first actually elastic analysis, and then we finish our design, and then we check with this direct analysis method. And after the design, we get all the axial loads, and from those axial loads we can accurately determine what amount of reduction of stiffness should be there. Then we applies those reductions of stiffness values, and then we run again. And when we run again for different load combinations, remember we run for load combination, not only for dead load or only for lateral load. We run for combinations. So for different load combinations, when we run, so that may change your design. So when it changes your design, you have to iterate this process again, because every time there may be changing this sway ratio to second order sway by first order sway ratio. And this one I have mentioned probably already, that if the sway ratio for reduced stiffness case is less than 1.7, or for nominal stiffness case if it is less than 1.5, then the notional loads are minimum lateral loads. They are not additive to the other lateral loads. Otherwise, we have to add them. And so we have to actually we have to check this for each and every load case. So for some load case like dead load, wind load, and then notional loads, or dead load, earthquake load, and notional loads. So for each of these load case, the scenario may be different. But what we can simply do is that to be conservative, we can add this notional load to all the cases. So that will make our life easier. So this is the summary. I think I have already said all of these. Like direct analysis method, K is always 1, but in effective leg method, we have to go for stability analysis to determine the value of K. Direct analysis method, we actually analyze the structure for P delta, P large delta, and P little delta effects. And in effective length method, we calculate some factors to consider P delta effects, B1 and B2 factors, and we apply them. So that's kind of approximate way, indirect way of considering these effects. In effective length method, geometric imperfection is not considered. Uh, there is a provision for notional load, but that is minimal. For when actually effective length method is not valid, first order no, second order effective length method is not valid when sway ratio is more than 1.5 for unreduced stiffness values. If it is more than 1.5, then effective length method is no more valid, no more allowed. You have to go for direct analysis method. Loss of stiffness under high compression loads are considered during analysis. And by all these provisions in direct analysis method, the net effect is that it amplifies second order forces and the results are very close to actual response. This is very important that serviceability checks should be while checking the serviceability limits, we cannot reduce the stiffness values. So we have to use unreduced stiffness. So what are the serviceability limit checks? So drift limits for wind and seismic cases. And if we want to calculate the building period, then we cannot reduce the stiffness. And for checking of vibration, then we have to use unreduced stiffness. So that was all about direct analysis method. In some of the softwares, the direct analysis method is already incorporated, like SAP. You can find direct analysis method is there, and I think there are user manuals. There are some manuals where you can learn how to use SAP to apply direct analysis method. So when we have large second order effects, we have to go for direct analysis method. And this understanding is very important. Now, so that was the second topic. Let's talk about seismic provisions. Let me first admit that I cannot cover all the aspects of seismic provisions comprehensively in this talk, because it will require long time to cover all the different topics, because this is so complicated, in a sense that is rather more complicated than the seismic provisions for reinforced concrete, because there are different types of systems in steel structures. They are mentioned here: moment frames, special truss moment frames, concentrically braced frames, eccentrically braced frames, buckling restrained braced frames, and spatial plate shear walls. And the behavior under seismic load and the desired response under seismic load are so different in these systems from one another, completely different, which is not the case for reinforced concrete systems. Reinforced concrete system mostly frames or dual systems, and the variations are limited. So it's rather easier to talk about reinforced concrete seismic provisions than for steel structures, and it's quite complicated. So another thing is that I'll not talk about the loading part. The loading part has already been covered, so I'll go straight to the design part. Let's see some pictures of different types of systems. So moment frames at the top left. In the top middle, you have a spatial truss frame, and top right is concentric braced frame. Left bottom is eccentric braced frame. There can be many different configurations, both for CBF and EBF, concentric braced frame and eccentric braced frame. There are many different variations in configurations. And bottom middle is buckling resisting bracing system, and spatial plate shear wall is at the bottom right. So these are different systems, and I repeat, for example, the behavior of concentrically braced frame and eccentrically braced frame, the behavior is completely different under seismic loading. I will concentrate more on moment frames in this talk. But to begin with, what are the different mechanisms? What we actually, the desired mechanisms. For example, in the moment frames, in the ultimate load condition for extreme event of extreme seismic event, what we want, how we want the structure to behave, to respond. For moment frames, do you want hinges to form in the columns? We want the hinges to form in the beams. That's similar like reinforced concrete. We want strong columns, weak beams. We want the hinges to be formed in the beams so that the energy dissipates there, uh, so that it can still carry the gravity load. In case of concentrically braced frame, the understanding is a bit different. The understanding is that we want to have some structural fuse through which the energy will be dissipated while it will retain the uh, vertical load carrying capacity. In that case, we want the bracings to act like fuses. So we want the bracings to buckle and yield so that the energy is dissipated through the bracings, while the other members of the structure, they remain elastic. So this is very important. Usually what we understand that under extreme seismic event, extreme seismic loading, we have inelasticity in the structure. That's why we reduce the load by using response reduction factor R. But remember, we want inelasticity in certain members, not in all members. Even at the extreme event, we want certain members to behave elastically, while we want some other members to behave inelastically. So this understanding is very important. In case of eccentrically braced frame, the middle part of the beam, we want that to act like a fuse. So we want energy dissipation from there. Now, when we want energy dissipation, we want to make sure that we want to induce that type of internal forces in the fuse which actually dissipates energy. So, for example, we don't want it to fail in a brittle manner. We want it to fail in a ductile manner while it yields, it dissipates energy, but it doesn't fail in a brittle manner. So that's very tricky. We have to ensure that it doesn't fail in a brittle manner, but most of the energy is dissipated through the fuse. The fuse will not have brittle failure. It will have a ductile nature. At the same time, all other members will remain elastic. So that is the philosophy for seismic design for steel structures. Here is an example. This is called RBS moment connection. What is interesting, I hope you can follow, you can see what is interesting here. Please notice carefully that there is no local buckling. The curved lines you are seeing, those are not local bucklings. Those are actually the beam sections are reduced in those places. These are the place where we want the hinge to form. So this is intentionally the beam section is reduced. So this is called reduced beam section, RBS moment connection. So this is a special moment connection where we have very strong panel zone, that is beam column joint in the connecting part, that is panel zone. We don't want there any kind of buckling in the panel zone, and we don't want any kind of kink formation between the panel zone and columns. So that's why we want a protective zone on two sides of the column in the beam, so that the hinge is not formed very close to the column. So that is there we want to have a protective distance where the hinges can form. So that's why we intentionally reduce the flange width in those locations. So this is called RBS moment connection. Okay. Now, this is very important. We know about compact section. We know that width thickness ratios, that is slenderness ratios of the elements of a member. If those ratios are less than lambda p, then we call them compact sections. So we want compact sections in some places. And there is another terminology, that is seismically compact section. Not only lambda p, we want to be more conservative. We want to have another width thickness ratio, more conservative width thickness ratio is called lambda ps. So lambda p seismic, lambda ps. We want width thickness ratio to be less than this lambda ps to ensure that those seismically compact section will definitely yield. We don't even allow inelastic buckling in those. Uh, we want to be more conservative. So those are lambda ps, seismically compact. So the values of lambda ps are given in this chapter, in this seismically. This is section 1020, right? Chapter 10 and section 20, 1020. There, this table is given. The table number is 61018. The limiting width thickness ratio for seismically compact sections. So I'm showing only the unstiffened elements. For stiffened elements, and there are other values for stiffened elements in the table. Now I'm introducing some concepts. So I've talked about compact sections, seismically compact sections. So in the code, it is written for which type of system, in which member we want the member to be seismically compact. So when we, in the code, certain member is mentioned that this member should be seismically compact, we have to check those limits. Now I'll introduce another concept, but this is, I think you are familiar to this, overstrength factor. Now, the R values, I think you already know how we come up with these R values. So the R values, actually there are two parts. One is R mu, that is ductility factor, and another is omega naught, which is overstrength factor. Why? The concept is if our structure would have been completely elastic, then under the application, under some seismic event, the base shear that would come onto the structure is VE. Say our structure follows the dotted line, which ends at E. If the structure were completely elastic, in that case, the behavior would have been linear, then the structure would collapse at the point E, and the base shear that it could sustain would have been VE. But we know that we cannot design like that. We cannot design our structures as elastic. So we allow inelasticity. So if our structure would show a bilinear behavior, that is elastic, perfectly plastic behavior, then we could get the blue dashed line. In that case, the energy that our structure could sustain, the amount of energy The same amount of energy it could sustain, like the elastic case, in reduced load. In V, if the base shear were Vy, and if our structure could undergo deformation up to delta M, so possibly the same amount of energy it could sustain. So that is the concept of inelastic design. But in real case, what happens? The structure doesn't behave bilinearly. The structure behaves non-linearly, like the solid blue curve. The structure remains elastic up to only point S. So what we do, we design the structure for Vs. The base shear is Vs. We assume the structure has the capacity only up to S. So we become conservative. So this part from point S to point Y, this is kind of reserved strength. But we have to understand one thing. This is not only reserved strength. This is the actual case. So in reality, although we design our structure for base shear Vs, and we become conservative to think that the capacity is S up to Vs, that is the capacity, and at the same time we assume a deformation like delta M, but actually what happens during the earthquake, the load actually comes. The load comes up to Vy. So as I said, we want some portion of our structure to go through this deformation. It takes most of the energy, and the rest of the structure remains elastic. So what happens? The portion that shows elastic ductility, that also has to go for higher level of force. So on those portions of the structure, actually they have to sustain V up to Vy. If we design in such a way that the structural fuse components, they cannot sustain Vy, how will they experience a deformation up to delta M? So the structural fuse items, those items which we want them to undergo a large deformation, at the same time we have to make sure they don't collapse early. So we have to make sure they have enough strength so that they can sustain the load up to Vy. So we have to ensure both. So you see, we have to ensure the strength, but at the same time we cannot make it too stiff. We want to make it ductile and flexible. So two different things. We want the structural fuses to be ductile and flexible, and at the same time we want them to sustain at least the force level up to Vy. That's why the portions that works like structural fuse, we design them not for the for Vs, not for the base shear, regular base shear. We design them for Vy. We multiply that with omega naught over strength factor. So this is very important. That's why we have this over strength factor in seismic provisions. We have to, for certain components, to design certain components, we have to amplify the force. This is called amplified seismic load. Okay, so think it in this way, that there are certain components which we have to design for this phase 3, and there are other components which will be designed for phase 2. Okay, so the portions that we design for phase 2, we ensure that they have enough stiffness. The portion we design for phase 3, we ensure they have enough ductility, and flexibility, but they have enough strength as well up to Vy. So that is very important. So in AISC, in these seismic provisions, this is the basic philosophy. That's why there are so many different types of provisions, because there are so many detailing that are related to these to make to how we can make the structural fuses ductile, and what the connections with the other parts should be. So these are very important things. So this is the amplified seismic load. We have to the horizontal portion of the earthquake load E, not the vertical part, not EH, the horizontal part. E shall be multiplied by the system over strength factor omega naught. Now, where can we find omega naught? In the loading chapter, that is in chapter 2, part 6, the same table where we find the response reduction factor R. In the same table, we have for different building types, we have this over system over strength factor omega naught. So we can use from this table. If steel systems are so versatile that we may even get some new system for which there is no value mentioned in the table. So for new types of steel structural systems, if we don't have any reference, then we can by default take omega naught as 2. You see, for building frame system, for braced frames, eccentrically or concentrically braced frames, omega naught is always 2. For moment frames, omega naught is 3. So we have to increase to 3 times seismically, amplified seismic. Now, this one is also important. This is required for connections. So we are applying load. We are applying amplified load on these systems. And we have to understand that we have reserve strength. So Fy, the capacity, actually material strength that we define, while defining Fy, we actually become very conservative. Fy is a conservative estimate of material strength. Now, we know that materials have reserve strength. So that reserve strength is reflected here. This is called expected strength. So expected strength we multiply with some factor more than 1 with Fy and Fu to calculate expected strength. So for some components where we apply amplified seismic load, at the same time we take into account the what is it called, that the capacity, it has reserved capacity. Okay. So now we talk about a little bit about different seismic provisions. So these provisions are applicable for any kind of frames, OMF, IMF, SMS. So like bolted joints, all bolts shall be pretension high strength bolts and shall meet the requirements for slip critical fairing surfaces with a class A surface. Remember that there are 2 types of bolted joints. One is slip critical type, another is bearing type. But for seismic provision, we have to use slip critical type, where the surface quality should be class A. Okay, we cannot use bearing type connections. The nominal bearing strength at bolt holes shall not be taken greater than 2.4 dt Fu. So this is the limiting value. Welded joints, all welds used in members and connections shall be made with a filler metal that can produce welds that have a minimum Charpy V-notch toughness of 27 joule at 18 degrees centigrade. So we're talking about some tests. So the metal, the filler metal, the welding metal, weld metal, that has to be tested. And if we have manufacturer certificate, that is okay. But if we want, if it is not, it doesn't carry any certificate, then we have to go for this Sharpie V-notch toughness test. Um, I think many of you have experience of this testing in the SM lab. We do this testing in our second year, level 2. So, and I think I should mention about another thing which I possibly didn't include in these slides. It's pre-qualified connections. The seismic provision mentions about pre-qualified connections. That is, we can connect beams and columns in many different ways, but some of the details are already pre-qualified. They are tested. So there are manuals for these types of pre-qualified connections. AISC has a publication, most probably Appendix N of AISC, of AISC 360, and there may be another publication of AISC where all the pre-qualified connections are shown. So we can use those pre-qualified connections. If we don't use those pre-qualified connections, if we want to use some other type of connections, then we have to go for all these tests and justify the use of those connections. Then they will be considered as pre-qualified. So column strength, depend on the actual vertical force that is coming onto it, gravity load, by capacity. So here load combination will include amplified for column. For column, we have to always take amplified seismic load. The required axial compressive and tensile strength shall not exceed either any of these two, axial compressive and tensile strength. The maximum load transferred to the column, considering 1.1 Ry, or there's another value, times the nominal strength of the connecting beam or brace element. So here we are talking about the strength of beam and brace. So we want the hinge to form in the beam or the brace, not in the column. So maximum load transfer to the column from the beam should be restricted to these values. The limit is determined from the resistance of the foundation to overturning uplift. And there, the applied load must be such that the overturning doesn't occur. Okay. So these are basic things. Now column splices, welded columns, this is very important. Welded column splices, that is, we don't want columns to fail. So we are very conservative about that. Welded column splices that are subject to a calculated net tensile load effect determined using the load combinations, including the amplified seismic load, shall satisfy both the following requirements. So splices, we want to add two column sections together to make a column here, splicing. So to calculate the capacity of the splice, we have to consider amplified seismic load. And the conditions are: one, the available strength of partial joint penetration groove welded joints, if used, shall be at least equal to 200% of the required strength. So from the calculation of the loads, the amount of load that is coming onto that section, the capacity of the PJP joint should be twice of that when we are taking amplified seismic load. So we are that conservative about columns. Okay, we don't want to hinges to form in the column. That's why we were so conservative. The available strength of each flange splice shall be at least equal to half of RYFYAF, that is flange area multiplied by yield strength multiplied by expected strength factor, or there is for ASD there is another amount as appropriate, where RYFY is the expected yield stress of the column. Okay, so here we are becoming conservative in a different way. Here we are calculating the strength of splice, flange splice. But while we are calculating the strength of splice, we have to consider the strength of the column. So we have to make sure that the strength of the column while splicing, the strength is not reduced. That's why we have to consider the reserve strength of the column. So we are not giving any check on the column. We are giving a check on the splice. But for that, we have to understand what is the strength of the column. And when we are considering that, we are considering expected strength, not the usual design strength. We are magnifying the strength to consider the reserve strength because we want that reserve strength to work. Okay, columns not part of the seismic. This is very important. So there may be columns that may not be part of the seismic resisting system, but they have to undergo the same amount of deformation. We have to make sure that they don't fail because of the deformation. Although they don't take the load, that's why you don't design those columns for the seismic loads. But we have to design the columns for seismic deformation. So we have to ensure that those leaning, these are called leaning columns. These leaning columns have the capacity for deformation. So for that, what are the requirements? The splices shall be located 1.2 meter or more away from the beam to column connections. So if any splicing is needed, of course, splicing is needed. So the splices will be provided away from the connection. So if there is any weakness at the splice, so that doesn't occur at the maximum moment, location of maximum moment. When the column clear height between beam to column connection is less than 2.4 meters, splices shall be at half the clear height, so in the mid height. The required shear strength of column splices with respect to both orthogonal axes of the column shall be MPC, that is plastic moment capacity, divided by H. That is, then we get the load, the force, as appropriate, where MPC is the least nominal plastic flexure strength, lesser nominal plastic flexure strength. So in both directions, in weak axis and strong axis, we get two plastic moment capacity. So this is the lesser one, so weaker, and on the weaker axis. So we have to calculate the force considering that the plastic moment capacity will reach in the columns. Then we'll get this force. We'll design the splice for that force. So that is the concept. Even for columns that do not participate in seismic resisting, lateral load resisting system, SLRS. For them, these are the conditions. There are other conditions. There are many more conditions. I'm just selectively picking some to describe. So for SMF, special moment frames, there are some conditions for beam to column connections. What are these conditions? Beam to column connection, I'll show some pictures of beam to column connections step by step, how they're in the field at the site, how we prepare a connection. Beam to column connection used in the seismic load resisting system SLRS shall satisfy the following three requirements. The connection shall be capable of sustaining an interior drift angle of at least 0.404 radian. So we want to make sure that a rotation, significant amount of rotation it can sustain. Second, the measured flexural resistance of the connection determined at the column face shall equal at least 0.8 MP of the connected beam at an interstory drift of 0.04 radian. First of all, uh, originally the connection has to sustain the plastic moment capacity. But when we apply this rotation 0.04 radian, at that point even, it has to sustain, it has to has capacity of 80% of plastic moment capacity. Third point is the required shear strength of the connection shall be determined using the following quantity for the earthquake load effect. So for shear force, the capacity, while calculating the capacity, the plastic moment capacity is again increased by the expected strength factor, that is the reserve strength factor, and then again with a factor of 1.1. Then we are dividing by the length, and then we are getting the earthquake load, E. For designing connection, so this is coming from the connecting beams. So we'll apply these loads at the connection and we'll design the connection. Okay, then protected zone. I talked about protected zone, that we don't want the hinges to form very close to the beam column connection. If it forms very close to the connection, then what happens? There is quite significant amount of rotation that causes kinks to form between the connection and the column, and that causes inelasticity in the columns. So we want to have a certain amount of protected zone so that the hinges form in the beams, not very close to the connection. That is the protected zone. The region at each end of the beam subject to inelastic straining shall be designated as a protected zone. Within the protected zone, discontinuities created by fabrication of erection operations, such as tack welds, erection aids, air arc gouging, and thermal cutting, shall be repaired. Remember, in the protected zone, where we want elastic straining to happen, we don't want any kind of brittle failure. So if there are some imperfections, like something sticking to that joint, that region, some tack weld, something sticking to it, some erection aid, that may cause some extra stresses, and that may cause brittle type of failure, like something may punch through the web. So we don't want that to happen. So you have to be very careful. Welded shear studs and decking attachments that penetrate the beam flange shall not be placed on beam flanges within the protected zone. Decking arc spot welds as required to secure decking shall be permitted. So any kind of extra stress that can come from other attachments, you should avoid in the protected zone. Welded, bolted, screwed, or shot-in attachments for perimeter edge angles, exterior facades, partitions, ductwork, piping, or others shall not be placed within the protected zone. So, same thing. So, we have to be very careful about the protected zone. So, once we make the connection, uh, we we finish the construction of the connection, then we have to remove all the different types of attachments. So here you see the protected zone is in the beam and it is supposed to buckle. It is supposed to not, it is supposed to yield. That is, hinge is supposed to form there. But while hinge formation in the beam, that's why this is RBS, like you see, reduced beam section. While hinges form in the beam section, at that time there is a tendency, that is the panel zone, that is just the beam column junction, the panel zone you can see between the stiffeners. There is a tendency of buckling in the panel zone. So we have to design in such a way that this type of buckling is avoided. So we have to be we have to design, we have to have some requirements for that, and the code provides those requirements for panel zones. Panel zone of beam to column connections. As a minimum, the required shear strength of the panel zone shall be determined from the summation of the moments at the column faces, as determined by projecting the expected moments at the plastic hinge points to the column faces. The design shear strength shall be, and the allowable shear strength be. So that's it. And the nominal strength RV, and according to that. So what is important here, that we have to take the moments while designing panel zone. It is not sufficient to take the moments of the beam end moments that comes from loading. No, we have to consider the total plastic moment capacity of the beam. That is, we will, while designing panel zone, we will apply the plastic moment capacity of beam section as load on the panel zone. We'll assume that the beams will form plastic hinges, so there will be plastic moment acting on the beam end, and we'll apply that on the panel zone to design the panel zone. Okay, just we cannot use the beam end moments that we can get from the analysis from our models. So that is the moment that comes from the loads, applied loads. So we want to be very conservative, that the beam end moments are much lower than the plastic capacity. So we design in that way. But for extreme events, we'll assume that the hinges will form at the beam end. So that plastic moment will come as load onto the panel zone. So you have to design the panel zone in that way. The individual thicknesses T of column webs and doubler plates, if used, shall conform to the following requirements. So we provide quite we provide thick webs so that in the panel zone we don't get buckling due to the hinge formation at the beam end. So some details can be shown here. That's why we determine the web thickness in that way. And not only we use doubler plates, extra plate with the column web is shown here. That is called doubler plate, extra plate we attach with the column web at the panel zone. And as stiffener, we use continuity plates. So the continuity plates are at the same level of beam flanges. So they are called continuity plates. They're stiffeners basically. And we use doubler plate. So doubler plates shall be welded. Doubler plates shall be welded to the column flanges using either a complete joint penetration groove weld or fillet welded joint that develops the available shear strength of the full doubler plate thickness. So usually we go for a CJP, complete joint uh, penetration groover for doubler plate, or fillet weld for the whole thickness. So doubler plate and continuity plates are shown here again. Now, for the design of panel zone, the capacity, what capacity should we consider? So that is shown here. And the capacities are dictated by shear buckling. So that's why you can see all the 0.6 Fy. And you see that R is not considered here. We are not considering RFY, that is, we are not considering any reserved capacity, because we want to be conservative for the panel zone. Okay, so we omit the R, we have the Fy, and we have other terms, area terms for shear capacity. And one thing we, for high axial force, we deduct, again we deduct some values. You see, PR by PC, we deduct the capacity with these values. Why? Because these terms come from column shear force. When there is high axial force, uh, column shear forces will reduce the capacity of panel zone. Okay, the column shear forces will come from beam axial forces, right? So there will be, for lateral load, there will be shear forces at the end of the columns, and those shear forces will reduce the capacity of the panel zone. So for high axial force, we consider and we reduce those terms from the capacity. Okay. Then column beam moment ratio. This is simple. This is similar as reinforced concrete. In reinforced concrete, this value is 1.2. Here is 1.0. That is column moment capacity, plastic moment capacity must be at least the same as beam plastic moment capacity. So it's defined here, M star PC, the sum of the moments in the column above and below the joint at the intersection of the beam and column center lines, and M star PC is determined by summing up the projections of the nominal flexural strengths of the columns, including haunches, where used above and below the joint to the beam center line, with a reduction of the axial force in the column. So it is permitted to take, okay, the formulas are given. So here again, you see, while considering the capacity of columns, we are not considering the reserve strength. But when we have to consider the connections, say, the panel zone, those critical elements, we will design considering the reserve strength of column, considering the reserve strength of beam. So that comes rather like loads. You may think that we use R to enhance the capacity. Actually, that is not the case. To overestimate the capacity, that is not the case. When we actually calculate the capacity, we don't use those R's, reserve strength factors. But when we calculate some the capacities of the attachments like connections, panel zones, then we consider the beam or the column to have not only MP, plastic moment capacity, but multiplied by the reserve strength. Then we consider the reserve strength and we design the connections and the panel zones accordingly. Okay, lateral bracing at beam to column connections, braced connections. So this is still we are talking about moment frames. We are not talking about concentric brace frame or eccentric brace frame. The conditions are completely different for those cases. Those are billing frame system. Brace connections. Column flanges at beam to column connections require lateral bracing only at the level of the top flanges of the beams when the webs of the beams and columns are coplanar and a column is shown to remain elastic outside the panel zone. So we need to actually have theoretically the top flange will be under compression. That's why there is a chance of buckling. So we have to connect the uh, bearing bracing with the. We need a separate bracing for top flange. Unbraced connections. Then we'll call that in the connections where we'll provide bracing for the top flange. We'll call that braced connection. And where we'll not use that, we'll call that unbraced connections. A column containing a beam to column connection with no lateral bracing transverse to the seismic frame at the connection shall be designed using the distance between adjacent lateral braces as the column height for buckling transverse to the seismic frame and shall conform to other conditions in there. So for designing for seismic loading condition and for buckling, what should be the length that we should consider as length of the column from the point where there is lateral brace to the another point where there is lateral brace. From the point of lateral braces, we'll consider the length of the column. So that is the condition. The required column strength shall be determined from the appropriate load combinations, except that E shall be taken as the lesser of the amplified seismic load or 125% of the frame available strength based upon either the beam available flexural strength or panel zone available shear strength. This is interesting. We'll design column not for only seismic load E. We have to amplify it. By how much? By omega naught over strength factor. For moment frame systems, moment frames, omega naught is 3. We have to amplify seismic load 3 times. Or what we can do, we can calculate the beam capacity and we can multiply the beam capacity. The beam must be capable of resisting the seismic forces, and then the capacity that the beam needs, the plastic moment capacity that will provide at the beam level, we have to increase that to 125%, and then we want that at least that amount of capacity in the column or the panel zone shear strength capacity. So the columns, in other words, column capacity must be at least 125% of panel zone shear capacity or the beam capacity. We'll design in that way. If we design like with amplified seismic load, then the capacities must conform to this limit, this one. Okay, and another important point for columns, the slenderness ratio shall not exceed only 60. Remember, yesterday we talked about L by R ratio 300 for tension members, 150 for compression members. But since this is compression and flexure, combined flexure and compression, L by R ratio must be less than 60. Okay, lateral bracing for beams. Both flanges of both flanges of beams shall be laterally braced with a maximum spacing of LB beam bracing spacing with 0.086 RYE by FY. Now, what is RY? Oh, radius of gyration in weak axis, about weak axis. So this comes from actually This is related to L by R ratio from buckling consideration. So we know that Euler's critical buckling formula, from there it comes. So that's why it is related to radius of gyration E and Fy, and there is a factor. Lateral braces shall be placed near concentrated forces, changes in cross-section and other locations where analysis indicates that a plastic hinge will form during inelastic deformations of the SMF. So usually we do that. We provide lateral braces near concentrated forces or when there is any abrupt change in cross-section. The required strength of lateral bracing provided adjacent to plastic hinges shall be Pu equals 0.06 mu by H naught, or Pa equals, for ASD and LRFT different. Anyway, for LRFT thing, that is the ultimate moment for ultimate load condition, the moment that will come onto it, divided by H, we get the force, the axial force. So that force, 6% of that force, we want the lateral braces to withstand 6% of that force. The force that will come on the structure for ultimate loading on the beam as moment, where H naught is the distance between flange centroids. So that is a little bit more than the web height. So those were some provisions related to SMF. There are many more. I just skipped many of those provisions. I just selected some provisions to discuss today, but this is this is not comprehensive at all. And there are so many other issues like modeling issues, like analysis issues, how to consider loads, I mean, what forces should be considered to design a particular component. There are many different issues that there. So the seismic analysis of steel, say, moment frames, only this topic, it requires multiple of sessions. So I'm skipping many things. Please pardon me for that. I tried to cover some important issues. That's it. For intermediate moment frames, still there are many different issues are there, but I have picked some of them. So beam to column connections similar to SMF. This is wrong, not SMR, similar to SMF, except that required interstory drift angle shall be a minimum of 0.02 radian. Remember, while designing beam to column connections for SMF, we have to consider a rotation of 0.04 radian. In case of intermediate moment frame, that is less, that is 0.02 radian. We have to consider the protected zone similar to SMF. We have to consider beam column limitations similar to SMF. Beam flanges, abrupt changes in beam flange area are not permitted in plastic hinge regions. Continuity plates shall be provided, but doublet plates may not be provided. Recently in AISC 2016, continuity plates are optional even for SMF. So there is a big change in the code recently in AISC, but in our code, continuity plates should be provided for SMF and for IMF. Lateral bracing of beams, both flanges shall be laterally braced directly or indirectly. The unbraced length between lateral braces shall not exceed, in the previous case, it was like 0.086 probably, and this is 0.17, almost double of that. In addition, lateral braces shall be placed near concentrated loads, etc., etc. This is similar to SMF. Okay, column splices, the conditions are similar to SMF. So, but there are some provisions missing in IMF, like provisions related to panel zone. In case of SMF, panel zone design is quite rigorous, but in IMF, We don't need to be that rigorous about panel zones. That's related to IMF. OMF, beam to column connections. Beam to column connections shall be made with welds or high strength bolts connection. These are the seismic provisions of OMF. Remember, there are systems where we don't need to follow these provisions either. We can design without following these provisions. In that case, we have to consider R3. But if we takes these provisions into account and design OMF, then the value of R will be like 3.5, something more than 3. So that's the difference. Beam to column connections shall be made with welds or high strength bores. Connections are permitted to be fully restrained or partially restrained. So even for seismic case, partial moment connections are allowed for OMF. Welds, complete joint penetration groove welds of beam flanges, shear plates, and beam webs to columns shall be demand critical welds. Now, demand critical welds, like these are, it's written here. They shall be made with a filler metal capable of providing a minimum Charpy V-notch toughness of 27 joule at 29 degrees centigrade. A little bit different. Previously, we talked about 27 joule at 18 degrees centigrade. It is 27 joule at 29 degrees centigrade. So this type of wells, when we provide filler material of this toughness, that is called demand critical welds. Okay. Now, continuity plates, when FR moment connections are made by means of welds of beam flanges or beam flange connection plates directed to column flanges, continuity plates shall be provided. In BNBC 2020, that is, which follows actually AISC 36005, their continuity plates were a requirement even for OMF when flanges, beam flanges are welded to the column flanges. Okay, so this is all about. I skipped many things. I again admit I skipped many things. I just selected some points. So these are related to OMF. Now I want to finish my talk with these pictures. These are step-by-step construction steps, welding steps, basically welding steps. How beam flange should be welded to the column flange for CJP weld, complete joint penetration in a special moment frame. So suppose we start with the top left picture. There we have the beam, but this is not the complete joint. The joint is not complete yet. The welding has to be done. The beam is connected to the column flange through bolted joint. Okay, so through bolted joint, and the plate, this gusset plate is welded to the column flange. Usually this plate, the column comes with these plates jointed from the factory by submerged arc welding probably. They come from the factory like this with these plates with the bolt holes, and the beams are connected to the columns and then bolted at side like this. And you can see there is some holes near at the web level and near the flanges. These holes are called weld access holes. So because we have to weld the flanges, we need some holes so that the welding electrode sticks can enter. So these are called weld access holes, and there are many requirements for them for seismic provisions. How the access holes should be, what should be the shape, what should be the dimension. These are all there in the code. So please follow them. I didn't cover them. So these are the standard access weld access holes. You can see. So now in the second picture at the top, you see at the bottom, for bottom flange welding, some backing has been provided so that some backing, some metal steel is placed under the flange, bottom flange, and tug weld. So that is attached to the bottom flange. Some tug weld has been done, have been done. So that is the backing material. Now some weld tabs have been placed. After placing the weld tabs, in the next picture you see that actually the welding complete joint penetration CJP groove weld. There is groove, you can see the groove, and the complete joint penetration is done in phases, in phase by phase, little by little. And in the left bottom corner, you can see the CJP is complete. For this reason, to complete the CJP, that is the access hole is required. That's why that so that we can use the stick, electrode stick, to weld. Now, after doing that, the backing material is actually removed, and all the weld tabs and backing materials, they are removed. You remember it is mentioned that in this protected zone no extra attachment can be there. All the attachment that are used during construction should be removed, so the backing material is removed. In the middle bottom picture you can see the top flange. Here again you have the backing material, and this is being prepared for the welding. And in the last picture you see the bottom flange is completely welded. The backing material has been removed, the weld tabs have been removed, and it has been ground properly. So this is the complete CJP welding. And after that, the requirement of the code is that this should be pre-qualified, John. The requirement is that the welding must be tested by non-destructive testing, NDT. So that is the complete process of welding flange bottom, the beam flanges to the column flanges. So I thought this is interesting. That's why I just covered them. So that is the end of my lecture. So I've covered some topics on connections. I covered direct analysis method, and I covered some provisions of seismic provisions for moment frames only. I didn't cover materials, seismic provisions for brace frames, concentric brace frames or eccentric brace frame, or special truss moment frames. I didn't cover those topics because all of them are so different. Each of them requires a lot more time to cover. So the questions, I have many questions probably already. So again, steel structure shed. This term is not there in the code. A steel structure shed building located in site class as D. Okay, this is site class, sol condition. And zone 4. Okay, from BNBC 2020, I will consider this as special steel moment frame. Okay, then the steel section have to be seismically compact. Not everywhere, not everywhere. The code mentions where the steel sections have to become seismically compact. Okay, and this will create significant material weight increase and costing, as the seismic effect for steel shed building is not much severe compared to multi-storied building. What do you say? And this will create and as the seismic effect for steel shed building is not much severe compared to multi-storied building. If I design the building with general non-compact section as per AISC code and maintain all serviceability, will this building be okay? First of all, how did you say that as per AISC you'll use non-compact section? I don't understand that. If you have to consider the seismic provisions, even in AISC, AIC requires you to use seismically compact sections for columns, for panel zones, for these areas, right? So you cannot avoid that. For second order effect, AC has referred to response spectrum analysis. On the other hand, AISC 36005 chapter C has referred to direct analysis. These are completely different, right? For stability analysis design on as response spectrum analysis is linear analysis and direct analysis is nonlinear inelastic design. Which method have to be followed? If I follow AISC, then do I have to design every building with direct analysis? You mean every steel building, right? So you have to follow AISC. And in AISC, in present building code BNBC 2020, you don't need to use direct analysis method, but in AISC 360 2016, direct analysis method is the primary method. That is the suggested method. That is the preferred method. So I would recommend all steel structure designers to get accustomed to this direct analysis method as fast as possible, because in near future this will be the preferred method of analysis. So it will always be better if you follow direct analysis method for designing steel structures. Okay. In Bangladesh, most of the real structure is sheds. Yeah, you mean 1 or 2 story height, right? They could be moment frames. They could be you mean truss at the roof, right? Okay, but that has to be truss moment frames. There has to be some lateral load carrying system. In Bangladesh, most of the steel structure is gable frame, and there are some gable frame system too. Yeah, gable frame consisting of column, rafter, purling, sheet structures. In AISC, for such type of structure, different type of allowable horizontal sway, h by 60 or to h by 100 is provided in Design Guide 3, serviceability. Can we consider allowable sway as per AISC h by 60 to h by 100? So much. So this is quite a lot, h by 60 or to h by 100. H by 500 for gable frame is too much conservative. H by 500 is not required for seismic loading. H by 500 is for wind loading, and for 1 or 2 story height under wind loading, it will not go. It will be the sway will be very small. Allowable sway for gable frame structure as per BNBC 2020 is becoming big question in steel structure gable frame design. I don't agree with you. H by 500 is not recommended in BNBC. It is only for wind loading combination. And for gable frame structures, the soil will be much smaller for 1 or 2 story buildings. Okay, and then rather up Uplift is a major concern for low height cable frame buildings. The suction. But I have to check this H by 60 to H by 100 for gable frame. Design guide 3. Okay. But in the AISC 360, there is no such provision. What is the standard procedure to check the steel plate material strength? By coupon test. Is it right procedure to cut material from the finished dissection product, or it should be checked before it is welded? It can be either, but you should collect the sample from some place which is away from the welding. Because of the heat of the welding, there will be some residual stresses. Okay, so the better practice is to collect the samples before welding, and you collect the coupons. We prepare coupon for the testing. Sir, we didn't get any dynamic analysis of structure. Yeah, I didn't cover that. Do you have any plan on this session? I see in this whole series, there is no session on dynamic analysis. I didn't notice that. It will be better for us if you could manage 2 dynamic analysis sessions on RCC and steel structures. Thanks. I don't think it will be possible this time, since there were many topics that we wanted to include in this series of webinars, but we couldn't. So dynamic analysis is one of them, like analysis for flat slab design. We couldn't include that. So there are many topics we couldn't include because of limitation of time. We have to finish by probably July, in mid-July. So we cannot cover these this time. Hopefully in future there will be opportunities when we can cover these topics too. Is it required to check the slenderness of flexural members for compression? Yes, of course. There are limits for that. Is there any size and thickness of steel beam and column that has a fire rating of any kind? I didn't cover this part. Yeah. For example, W200 by 8 size provides monomer. It doesn't depend on the size, I suppose. It doesn't depend only on the size. Okay. So I have to check. It doesn't only depend on the size. What is the allowable sway limit for single story industrial luncheon? The same question. There is no separate limit. The limits you have already learned, those are the limits. There is no separate limit for single story industrial stretch structure. Sir, can you explain what amount of partial fixity we should consider and how to determine this? This is a very tricky question. There are many literatures on this topic. There are many papers, many manuals. So depending on the connection type, there can be many variations. And all those various types of connections show different moment rotation relationship. So usually for different types of partially restrained connections, peer connections, there are some pre-qualified connections and there are some manuals for those pre-qualified connections, and there the moment rotation relationships are given. You can find them in literature. Then from literature you can use them in your models. What is the R value of single story steel roof shed supported on masonry wall? This will be basically lateral load resisting system will be unreinforced masonry. So the R value is before unreinforced masonry. Actually, this is not recommended. This is not a seismic system. Lateral load resisting system, unreinforced masonry walls. If you reinforce, then you can you can treat it as a lateral load resisting system. Dear sir, Assalamu alaikum. Can we follow to check the serviceability of steel building AISC Design Guide 3 Serviceability Design Consideration for Steel Buildings and AISC Design Guide 7 Design Guide Industrial Buildings Roofs to Anchor Rods? Because I think there is a deficiency of information in BNBC 2020. Furthermore, section 10.12.2 of BNBC 2020 has referred to the section 1.4 and 1.5.6 as well as section 1.2.5 table 6.2. I agree with you, Mr. Bari. Yeah, we can talk more about that. I completely agree with you that these are the deficiencies in BNBC 2020. You see, BNBC 2020 had to cover all types of materials like concrete, steel, masonry, bamboo, timber, everything is there in the BNBC. So the BNBC could not be as extensive as you like to treat any individual type of structural material. For steel, even in the chapter 10, only one chapter is there for structural steel design, but that is so huge because all of AISC 3, almost all of AISC 36005 had to be included there, and there are seismic provisions, so different publication, and there are other publications for erection and fabrication. So all those different publications, the summary of those publications, so the gist of those publications had to be included in the BNBC. So in the BNBC, it was impossible to consider everything. So you are absolutely right that BNBC 2020 is not comprehensive enough comprehensive enough to consider all the different issues related to structural steel design. So definitely BNBC 2020 is open in the if you can justify use of some other standard, and if you can show that the performance of the structure is acceptable, BNBC 2020 does not restrict you from using those standards. I think the same question is repeated again. In general, if there are any isolated footings that is considered as pin in the analysis, is there any calculation or considerations that an isolated footing considers as fixed support of an existing single-story shed building? If yes, then please share the consideration. Okay. It doesn't depend only on the footing type. It depends on how you are anchoring your steel sections to the footing. It rather depends more on that than on the footing. Okay, so that is important, I think. In AISC 36005 for compression, KL by R is recommended 200, but why 150 in BNBC 2020? For compression, is it 200? In AISC 36005, I thought BNBC followed completely AISC 36005. I have to check if it is 200. Could you please show us some practical example picture of slip critical and bearing tap connections? Probably in future. In future, or what could be, I don't know how. Right now I don't have with me. So probably in future I can show. Practical example, right? So I don't have any photographs with me right now. As steel structure is weak in regard to fire resistance, how fire resistant rating BNBC could be met in steel structure buildings? There is a short section on fire resistance of steel structure, but I found that that is not comprehensive enough again. So that's why actually I skipped that. So this is a long story. So What best I can say that for low-rise structures like one-story, two-story structures, the as fire section in part 4 of BNBC, the restrictions are not that strict. There we can go for steel buildings without any other treatment. But if we go for multi-storied steel buildings, we have to think for some kind of coating or cover on the steel. From where we can get easily the specific joint connection detailing for different steel moment frame. There are publications of AISC. There are publications like different types of pre-qualified. There is a dedicated publication on different pre-qualified uh, connections. Dear sir, for three-dimensional model of steel structure substructure should incorporate or not where considering base plate connection is pin. If you consider base plate connection as pin, modeling of substructure, it depends. If the soil is too soft, that soil structure interaction becomes important. But for steel structure, soil structure interaction is seldom governs. So I don't think this is important to model the substructure. Please explain shortly as depend on BNBC 2020 overall sway of gable frame. Same question. We don't have any separate provision for gable frames in the BNBC. Maybe design guideline 3 of IAIC has some provisions we have to see, but not in the BNBC. Have there any provision for a steel structure where connection not specifically designed for seismic reasons? So you mean existing structure that doesn't have proper detailing and you have to consider seismic provisions, then you have to go for retrofitting. For retrofitting, there are other publications of AIC. It seems that the presentation slides have been modified. Right. I'm sorry. I will supply these slides to Dr. Prabudha and Maria, and I would like to request them to uh, upload this new file so that you can download them. I'll do that. Sir, can we get these lectures, videos, if we get them? We are talking about these, and we need permission from Raju. If Raju permits, then they can be uploaded to YouTube or anywhere from where you can download. We have sought permission to Raju for that, and if Raju permits, then it will be provided.
Dr. Rakib,
Yes,
we actually received permission from Rajiv now.
I
So
see.
we have started uploading.
That's
It has
great.
not been, the videos have not been shared yet, but it will be they will be very soon.
That's a great news. Thank you, Dr. Prabhu, for that. So everybody will be happy, including me. I'll be very happy because I missed many lectures. I want to see them. Sir, can you explain some of the fire requirements I skipped? Because the fire requirements that are included in the BNBC 2020 for steel structures, I felt that they are not comprehensive enough. So that's why I skipped them. So hopefully in future updates, they will become better. It connect what connections of a truss is welded. If connections of a truss is welded, then the connection has to as pinned or moment connections. I'm sorry, no. They cannot be moment connections for truss moment frames. They can be moment connections, but that is the topic of special truss moment frames. So there are details for that. So just by welding a truss member to column members, does not produce a moment connection. There are other details, and that is discussed in the seismic provision of special truss moment frames. Either LRFD or ASD, what method do you suggest to follow? Obviously LRFD. There is no meaning using ASD anymore. I don't know why it's still there, because it doesn't make your life easier. It's all the same. So I'll obviously recommend LRFD. Is it possible to use steel plate shear wall for building frame system? For building frame system, this is not classified as building frame system. This is classified differently as special steel plate shear wall system, because yeah, uh, yeah, it is there. Probably I have to check, because the shear walls, steel shear walls will only take lateral forces, not gravity forces. So the gravity forces will be taken only by frame members. So that is building frame system. So I have to check if it is classified like that in our table. I think so. This is still building frame system. What type of structure will perform better in case of high seismic force? What type of structure will perform better in high seismic force? For steel structures, there are some advantages, because the steel structure is usually lightweight, because you are using thinner sections. So the weight of the whole structure is much less as compared to concrete structures. So that is one advantage you have with steel structure in high seismic zones. So from that point of view, steel structures are preferred, particularly for tall buildings too. So I think these are were the questions, and I have covered all of them. Uh, I myself is not satisfied with my lecture and with my answers. I have to study a lot more, because this is not a field of my specialty completely, but I tried to cover some important aspects of structural steel design. I hope that it is useful for you, and for those who are new to steel structure, new to steel structural design, I hope that this lecture may grow interest in you in steel structures, and those who are already practicing steel structural design, I hope that you'll get some new materials from this lecture, like direct analysis method, and I suggest you to go for these advanced methods and catch these methods as early as you can, because uh, these are the trends that will come in near future. So thank you so much for attending this lecture. Thank you.